Hi, um, we are now at the second screencast of chapter 9b, and very briefly I want to go back to what we were talking about in the first place. Set theory we are talking about is a mathematical science of the infinite. We already studied that. It studied properties of set, abstract objects that pervade the whole of modern mathematics. Language of the set theory in its simplicity, and we saw it is in principle simple, is sufficiently universal to formalize all mathematical concepts and thus constitutes the true foundations of mathematics with capitals. Okay, in chapter 9b we were talking about ordered pairs. And if I have two sets A and B, then the cardinal product A times B gives me a set of all possible combinations of all possible pairs. In fact, this is the universal relation because I have everything I could possibly combine. Now then we moved, instead of having two sets A and B, to one set S. This is S. This is S. X is element of the first S, Y is element of the second S, and then we define different types of relationships, which were the reflexive, symmetric, and transitive relation. Now, just very briefly, if set S consists of the numbers 1, 2, 3, 4, then a reflexive relationship means that at least these points are a subset of the relation. A symmetric relationship means that if the point 2, 4 is part of the relation, then 4.2 symmetrically is also part of the relation. And transitive relation was as follows: if 1 has a relationship with 3, 3 has a relationship with 2, then 1 has also a relationship with 2. You have this triangle construction. Now, this was what we did so far, and how do we continue? Well, first of all, I would like to introduce the concept of the equivalence, a word we will use quite often in this cast. Equivalence relation, and that is a relation that combines all three aspects. Okay, quite easy. Another relation I would like to mention is the void or empty relation. R being an empty relation. Wow. Then the third point is the point of the classes. Now, if I have two sets S and I have an equivalent relation between X and Y, then what happens is that this set S is going to be partitioned. It is going to be split up in two subsets, or three. Important is that these subsets do not are disjoint. They don't overlap. And if you have an equivalence relation, you have this kind of splitting up, this kind of partitioning. And we call this these subsets equivalence, the word again, classes. To give you an example, instead I'll take the set z of all the integers, so 4, 3, 2, 1, etc. And here again the same. And now the relationship I'm looking at is the relationship that x and y have the same remainder by division with the number 2. So for instance, if I look at the number 4, if it has a remainder 0, so it has a relationship with 4, having also a remainder 0, but also with 2 and 0 and so on. And you see already very quickly I am pointing at the even numbers, because they share this property that if I divide by 2 and so on and so forth, they all have a remainder 0. The others, 3 for instance, has a remainder 1, which is something it shares with 1, negative 1, and 3 obviously with 3 and 1 and so on. And now I'm connecting all and so on and so forth, all the odd numbers. So you see I have a subset of odd numbers and I have a subset of even numbers. They are disjoint and they make up together the set of the all integers. Now this is what we call equivalence classes.